So CAB. Just assume we did 9 experiments in the lab. 9 experiments in the lab with a feed solution that contains acetone and water. And then we are going to use isopropyl ether, I think. Ether as your solvent. So this is your feed solution. So our aim is to use this solvent to extract acetone. Extract acetone. So this is a chemical engineering problem. It has nothing to do with pharmaceutical chemistry, but acetone is a main solvent. We use this solvent to crystallize many API compounds. In that spirit, we are not skipping the we are not deviating from the subject that we are learning. Yeah? So in the industry, it's not only about manufacturing of products. They like to they try to make the process economic. Yeah, so they like to save money wherever they could. At the end of the experiment, if they could find a way to recover their acetone or any solvent in general, it's a money for them, because the acetone is also an expensive solvent. So nothing comes for free. So whatever they have, they will try to recover it. So, and then there are many ways to separate acetone and water. For acetone and water, we can separate using distillation. Distillation we will see after this liquid extraction. That will be the next topic that we are going to cover in this module. So distillation, that time we will know what is how to separate this type of fluid mixtures, but it's going to be very expensive. Very expensive due to the temperatures involved. Water has a higher boiling point and so on. So but if you use acetone and isopropyl ether, it's very easy to separate acetone from isopropyl ether. You can easily evaporate one of the compound followed by condensation, and then we can separate one of this compound easily. But anyway, you will know how to do these things from using distillation. I will, when I'm going to cover distillation, I will remind you this problem: acetone, water, and then isopropyl ether. So that time you will get some idea. But the whole idea for this experiment is like, we need to separate acetone from the water using isopropyl ether as solvent. And don't forget that the topic that we're talking now is liquid equilibrium. So everything is liquid. Acetone is in liquid mixed with water, another liquid, and isopropyl ether is a solvent, it's a liquid. So we are going to use one liquid to separate something which is dissolved in the another feed solution. So using isopropyl ether as solvent. So that's the current problem. And just assume we did already 9 experiments, and then we have at the end of the experiment, every time we get something called as extract, something called as raffinate, and each of them will contain 3 components: A plus B plus C. Extract will contain A plus B plus C. So let me show the value. So that's the value we got. This is your raffinate side, this is your extract side. If you want to make it like a flow diagram, we can say this is your extraction unit, feed solution, solvent, and then here, let's just assume this is your solvent phase. At the end of your experiment, you will have 2 clear separation. Yeah? So the top will be your solvent, which you can remove, and then the bottom will be your feed solution. So now we call this as how do you call it? Raffinate. Raffinate, even this one we call it as extract. So this extract will be enriched with your solute molecules. So it will, because we already moved a lot of solute from here to your solvent side, and this is called as a raffinate. So if I give you a table like this, so we did 9 experiments, and then this is on one phase and this is on another phase. If you don't know which side is your extract and which side is your solvent. Just look at the composition of your solvent. So wherever you see the higher weight percentage of your solvent, so that will be your extract side. So which means this part, the top part of. So you see 99, 1.2, you see 48.7, 16.5. So this is your extract side. But anyway, I won't ask you like identify which one is your extract or something. Yeah? I will give in the exam clearly what is what. So this is your raffinate side, this is your extract side. Say this. So these two are from experiment 1. So at the end of the experiment 1, you have your extract, you have your raffinate, and A plus B plus C, and A plus B plus C. The corresponding composition is this one in the extract side, and the corresponding composition in the raffinate side is this one. So it's this side. So this is your raffinate side. So, and just imagine we did our 9th experiment successfully. So you have your extract, you have your raffinate, A plus B plus C. Your extract will contain A plus B plus C. So both of these side are containing something, all the 3 components, and that's because some is partially miscible. Your solvent and your solvent in this case is isopropyl ether plus your solvent, sorry, your carrier liquid water, both are partially miscible. Yeah. So that's why you find something on both the sides. So your extract side will contain a bit of your carrier liquid, and your raffinate side will contain a bit of your solvent. So that's how your experiment works. And just assume we did 9 experiments. So this just the 9th experiment. This is the composition of your A plus B plus C in the extract side, and this is the composition of your A plus B plus C on the raffinate side. So this is one experiment, and then these 2 values are from one experiment. This one and this one are from one experiment, and so do this one and this one are from one experiment. So I have to use this word experiment because if not you will lose the track. Yeah. So obviously we are not doing any experiment in the classroom. I'm just saying like so you have some 6 numbers. So under all of like this 0.69, 98.1, 1.21, 0.18, 0.5, 99.32. Everything comes from one single experiment. Yeah. So there is. I'm saying this because at the end we are going to draw some line. We call it as a tie line. So only if you understand this, then you will know what is a tie line. A tie line is related something to what you are seeing at the moment. Yeah? The tie line is a line that relates the composition of 3 of your components in the raffinate side, and the composition of your 3 components in the extract side. We will come back to that once we finished plotting the data on the graph sheet, on the ternary diagram or equilateral triangle, whatever we can call it as. So I think I hope you all are following these ones. So this is a bit tricky. Yeah, I know the ternary plot is probably you are seeing this for the first time, but it's not difficult. Yeah. So here you have some number 37.1, 46.4, 16.5. It's the same. I already showed you like in the ternary diagram 40%, 50%. The remaining should be 10%. The same rule here. If you sum these values, whatever the remaining will be equal to 16.5. So that's how it works, and we are going to make use of this graph, and then we are going to plot it on a ternary diagram. Yeah, I will show how to do that now, a bit slowly. to next slide. Okay, it came. Oh, I put a question mark here. Why is that? Yeah? So just to remind you, use the same notation. Your solute goes to top. C is your solute. And then A is your, what is that? Carrier liquid. Please try to remember these things. Yeah? At least take a note, or maybe I can do a revision class myself, like 40 minutes we revise everything in liquid extraction, another 40 minutes we revise everything in crystallization. Why not? B is your solvent. So A is your carrier liquid, C is your solute, and then now we know isopropyl ether is your solvent, so this should be B. Sorry. So this should be B, and then water is your carrier liquid, so this should be A, and acetic acid, that's the one we are going to remove, that's your solvent, so C, so cap, and then your acetic acid is again C, water is A, and then your isopropyl ether is your solvent, so let's use the notation B. So I hope you all are following this one. So let's try to plot, say, which one to choose. Maybe this one, 13.3, 84.4, 2.3. So what is this? C, 13.3 weight percentage of C. So C is here. So this is 90s, 80s, 70s, 60, 50. So this is your 10 percentage of your solute or C. So where will be your 13.3? So this line is 12. So 13.3 will be somewhere around this line. I don't have a scale. The final exam you can use the scale and then just plot it here. So this is your 12, this is 14, so somewhere in between should be 13.5. So this line is 13.3 percentage of your C solute, and then your water is 84.4. Oh, this is so water is nothing but carrier liquid, so this is your 90 percentage C. So this is your 80 percentage, 80 percentage A, this is 90 percentage A. So 84 will be, this is 82, 84. So 84 will be somewhere around here. And this is the line we already draw. This is 13.3 percentage of C. And this is your 84.4 percentage of A. Whatever the remaining, that should be equal to your B value. So B is 2.3. We don't have to plot it, but I will just show you what is that. So your B is here. So this is your 0. This is your 0 percentage of B. This is your 2 percentage of C. So 2.3 will be somewhere near. So it will be around this line. So everything meets at one point. Yeah. So that's your point. So this point corresponds to this one. These three values, and then you can do the. So I will recommend you to plot all these values on one side of your graph. We will get some graph like this. So we call this as a raffinate arm, and then if you plot all these values here on this one, so maybe I can try to plot one value. So 1, 2, 3, 4, 5, 2.3. So 1, 2, 3, 4, 5. So let me plot 4.8. So these two values are obtained from the same experiment. So I'm going to plot 4.82. Let's plot that one. 4.82 percentage of C. So this should be somewhere again down here. This is 0 percentage C, 2, 4. So 4.82 will be somewhere around 5. So it will be somewhere in the middle. So this will be approximately 4.82% of what? C. And then the remaining is 93.28% of isopropyl ether. Isopropyl ether is nothing but your solvent. So 93.28. So this is your 90% line, 92% line. So 93 will be somewhere here. Oops. I'm sorry for such a horrible diagram. I am using a very cheap notepad. Yeah. So 93. Normally in the classroom, for me it's if you are in the UL, then I can take a very long scale. I can project this on the screen. I can put the scale, and then I can show that's the line that we are focused on. And then I can even draw a diagram using some board marker. Now it's a bit difficult, but it's okay, like okay, due to COVID I cannot see you, you cannot see me, you don't even know how I look like, I don't know how you all look like, but the good, and we don't have interactions like normally we should have it during the class time, but on the other, the good side is like we are in constant communication every time when you watch a video, which means you are listening more than during the normal time. You can play the video, pause the video, you can come back. If you don't understand, you can watch the video again. So that's why I think the interaction time is more than the normal time. At least I take it that way. So it's not a bad thing. Yeah. So let's do this plot. So I know you have to watch this, you are going to watch this video at least 2 or 3 times, because this equilateral triangle, it will make it will make you mental if you don't know what's this. You should know where is the 100% line, where is the 0% line of 3 of these components. If not, it's going to be really tough. Yeah, so it's going to, so just I know you will follow this maybe 2 or 3 times and watch the video 2 or 3 times, and then you will understand, or maybe you might even grasp it in the very first time. Yeah, but don't mix up with the numbers. Yeah, so try to pay attention. The corner of every triangle, that corresponds to 100%, and exactly the opposite base of the corner of the triangle, that should be 0% line. Yeah, so try to keep these things in the mind, and then you will get used to this equilateral triangle. It's not a big deal. So anyway, so this is your 93.28% of your B value, weight percentage. Everything we are talking in terms of weight percentage. So it cuts somewhere around here, this point. So, and even if you plot the other value, 1.9 of water, so what is that? So your water carrier liquid is here 100%. So this is a 0, and this is 2% of water. This is 2% water. So your 1.29 will be somewhere around this value. So this point is somewhere around here. Yeah. So that's this point corresponds to this value 4.82, 1.9, 93.28. Yeah, I hope you all can follow this one. So if you finished plotting all these values on this graph, you will get some curve like this. We can connect them. So this side we will call it as extract arm. And I hope you all remember, just now I said these two values are from one experiment. So what it says is like, it's this part 48.2, 1.9, 93.28, that defines the weight percentage of your each components A, B and C in the extract side. And exactly the other way, if you come to this table, 13.3, 84.4, 2.3 defines the weight percentage of each component on the raffinate side of the same experiment. So, and we plotted them, and the line that you connect these 2 points which you get from the same experiment, we call it as a tie line. So it's relating something with something that you got from the same experiment. Yeah, obviously it's relating the composition of your components in the extract side, and it's also relating the components on your raffinate side from the same experiment. Yeah, I think this is easy to follow, I think. And then, by the way, why are we plotting this one? Yeah, we can plot the same data on a normal XY graph sheet. I will show you in the next lecture. But why are we plotting this is like this graph, you need it to design some liquid extraction unit. We will solve a problem. It's going to be a big problem. Yeah, it might take 40 minutes. The way I am teaching, it might take even 1 hour. So I will solve that problem using the same data which you are seeing now in the screen, or maybe I might even take some new system. Why not? And then I will show you, if you have this curve, then from that you can plot. You can plot. You can, sorry, not plot. You can design some extraction unit, and you will do some engineering level calculations using a set of protocols. Those protocols has nothing to do with theory, but it will help you to design some liquid extraction unit. Yeah, so we will come back to that when we are going to solve some problem. And by the way, what the diagram which we got now, it's good to introduce something. So this curve A and B, so this type of curve, so this is this part, so we can separate, we can have clear separation. So that's the meaning of this curve. So this is another reason to plot this curve. So any point here, if you have any composition of A, B and C under this triangle, I don't know how to create a shade on this triangle. So we can get a clear separation, and anything above this line, this area, we will have a homogeneous solution, which means we cannot separate anything. So it will be like all the three solutions will be complete, all the three liquids will be completely mixed. So we cannot separate anything from anything. But from here, if you have any composition under this curve, we will have a clear separation. Yeah. So I thought to quickly summarize whatever we studied so far in this lecture, because this is a bit tricky one, so I thought it's not a bad idea to summarize everything. So this, we already learned how to plot an equilateral triangle. So I said which notations we should use. CAB, C is your solute, B is your solvent, and then B is your carrier, A is your carrier liquid. So you plot them on the three corners of your triangle, and then we particularly selected a system, acetic acid, which is mixed in water, or if you want you can call aqueous solution of acetic acid, plus isopropyl ether. So that's our solvent. So that's what we plotted. Then we got some graph like this, and then I said, so this side is your extract arm, and this one is your raffinate arm. If you don't know which one is your extract arm and which one is your raffinate arm, you see A is your carrier liquid, so the data points closer to carrier liquid, they must be your raffinate arm, and then the points which is closer to your solvent side, that should be the extract arm. Yeah? So take this one like a small tip. And then, so what's the purpose of drawing a ternary diagram? Yeah? So CAB, so in this graph you get something like that, and then so what it says is like, so whatever inside here, we will have a two phase. So if our liquid compositions are within this region, so we will have a clear separation. So we will have two phase. So at the end of your experiment, you will have an raffinate phase, and then you will have an extract phase, so we can separate them. So if our liquid composition are in any of this point outside this line, it will be only one phase, it's a completely homogeneous solution. So your ternary graph will help to identify the particular level of liquid composition at which we can achieve a clear separation. So that's one of the main advantage of using a ternary diagram. And of course, we are going to make some engineering level calculations using this simple plot. I will show you later, maybe in the next tutorial or lecture. I don't know how to call. So, and then don't forget, C is your solute, A is your carrier liquid, and B is your solvent. And then what else we can learn from this? Another thing that you can understand from ternary diagram, I didn't tell this during the lecture time. So CAB, if you get a graph something like this, so this is your two-phase region, and this one you don't see any line on this A and C. If you get some graph like this, it means A plus C are completely miscible and C plus B is completely miscible. So just by looking at the ternary diagram, you will know which of the two components are completely miscible. And another thing is like, let me go to the next page, it looks so confusing. C, A, B. So A and C are completely miscible at all compositions. So irrespective of the composition, like A plus B plus C, whatever the composition, A and C is completely miscible. And then here B plus C, irrespective of the composition of A plus B plus C, B plus C is completely miscible. So I will tell you few more, I will draw some more diagram that will give you some idea. Say we did some experiment, and then when we try to plot on a ternary diagram, we get something like this. So what does that mean? In this case, A plus B is completely miscible. So you will get this type of idea only if you try to plot different systems and then you look at the figure finally, then you will know, okay, I know this system A plus B is completely miscible and this will be my ternary diagram, how it's going to look like. Yeah? So in this case, B plus C, this is completely miscible, and then in this case A plus C, they are partially miscible. That's why we can get a clear separation. Remember, I said to you before, whenever we talk about liquid-liquid extraction, you have to think miscibility. If miscibility is good, separation becomes harder. If miscibility is poor, then separation becomes easier. And in this, go back to this diagram. In this diagram, A plus B is partially miscible. Yeah, and this particular type of system, so this type of system, let me draw it again here. CAB. So A plus B partially miscible, and then C plus B completely miscible, and also completely miscible at all compositions. And then A plus C completely miscible at all compositions. Yeah. So hope you all understand what do I mean by this. Yeah. So you have some two-phase region on A and B, connecting A and B, which means A plus B is partially miscible, and we don't have any two-phase region connecting A and C. That's why we are saying A plus C is completely miscible. So what I am saying is like how to interpret which components are miscible and which of two of these components are partially miscible. So that's what we are trying to learn through this ternary diagram. I can draw a few more diagrams for you, why not? So let's say something like this. You have a system like this. I'm going to draw only one line here. One line here. So what does this mean in this case? A plus B completely miscible irrespective of the composition A plus B plus C, and in this case A plus C is almost completely miscible except at few conditions, except at some particular composition. Same rule goes here. A, B plus C, B plus C almost completely miscible in industries. We will encounter all these different type of systems. Yeah, that's why I'm trying to plot this ternary diagram, but you should know how to interpret the ternary diagram. If I give you a ternary diagram, you should tell to me A plus B are completely miscible at all compositions, B plus C are almost completely miscible except at some compositions. So except at some point B plus C is completely miscible. So that's how we interpret that data. I can draw one more diagram. All the diagram, these are not hypothetical images. This type of system really exists in the world. So CAB, you might get something like that. So in this type of system, A plus B partially miscible, and then B plus C completely miscible, and then B plus C almost completely miscible, except at some point. At this particular fluid composition, you will get some clear separation. Yeah, so that's the meaning. That's how you have to interpret your ternary diagram. So having a knowledge of ternary diagram is really a big thing. Yeah? So it's also good for your CV. So then once you finish learning this, you must add it in your CV that like gained knowledge in ternary diagram, something like that. In fact, that's a big skill, and it's a big asset for your curriculum vitae. So it's not a bad idea if you are learning this bit slowly and trying to make a sense out of this. So whatever this diagram which I'm drawing now, that comes from experience, because you have to read a lot of book, read different type of systems, check the handbooks. They might have different type of system where you will get this type of like this one, this type of ternary diagrams, and then there you will understand which and which is partially miscible, which of the two components are not completely miscible. But anyway, since I know these tricks, I'm just saying it now. Keep it in your mind. I think most of the textbooks, they won't say this these points. Yeah, they will just show you some ternary diagram. This is the system, this is our data, that's my ternary diagram, it's going to look like. You won't see how to, they won't explain like, okay, if a ternary diagram is like this like A plus B is partially miscible, A plus C is not miscible. They won't say those things. Yeah, so try to follow these notes. So I'm going to draw a few more diagrams just to make you understand a few things, because the more diagram we interpret, the better. So let's plot one more curve. This type of systems exist. system exists in real world. Yeah, so in this case, a plus b are partially miscible, and then a plus c are almost completely miscible except at some composition at some point. It's the same rule applies here. So b plus c almost completely miscible except at some point. So try to remember this. I already said to you many times whenever I am talking about liquid-liquid extraction. So whenever we are talking about liquid-liquid extraction, the one thing you should remember is miscibility. So if miscibility is good, then separation, we are going to have a very hard time. Yeah? In fact, separation will not be possible if everything is completely miscible. If miscibility is poor, then separation is easier. So it changes in the other direction. So okay, one more thing I forgot to say. So this one we already saw this type of system, C, A, B. So this is the one we already plotted. So in this case, so whatever you see in this under this curve, so this is like a two-phase region. In this case, A plus B are partially miscible. A plus C completely miscible at all compositions. And then B plus C is completely miscible at all compositions. So this type of system, we call it as a type 1 system. Type 1 system where is something we call as a plus C and B plus C completely miscible at all compositions. So this one we call it as type 1 system. Few books they call it as a type A system. Yeah, I prefer to use type 1 system. And then okay, and then just to remind you, probably everything, even this type of system, everything under this region, we will have a two-phase, which means separation is possible. So this is your two-phase region, and everything outside, how to change the color. So everything outside, this is completely homogeneous. So homogeneous. So separation is not possible. We will try to solve some problem. Yeah? Then that problem will tell you how cool this graphite is. Yeah? So we can solve lot of engineering problems using this one ternary diagram. And then coming back to here, this diagram, just to show this region is a two-phase region in this graph. This is your two-phase region, just this one line, just to follow the whatever I'm drawing now. So this is your two-phase region. Everything else is homogeneous. Yeah, and then again here, pay attention, because you won't find this in any textbooks. They won't tell all this, I don't know, tips or tricks to understand this ternary diagram. So this is your two-phase region, and all this side, they are homogeneous. So So there are few more systems which are available in literature. So let's put CAB. There are this type of systems. So this is your two-phase region where separation is possible. Two-phase region, and any point on this side, they are homogeneous. And if you look at this graph, in this case, you see some line cutting here, A and B. So which means A plus B, they are partially immiscible. Again, B plus C, partially immiscible. Sorry, partially miscible, and then A plus C, again partially miscible. Forget the word immiscible, they are partially miscible. So keep those things in your mind. And then I can plot one more graph just to make you understand how to interpret or how to get the right level of information from a ternary diagram. Say something like this. This type of system exists, believe me. So what we are learning at the moment is liquid extraction, and through this type of different type of ternary graphs, what we are learning is the principles of liquid extraction and how the equilibrium plot will look like on a ternary diagram, and how to interpret from the or what type of information you can take from those ternary diagrams. Yeah? So this will take a lot of time if you read in the books to understand. If my ternary diagram looks like this, then I can say B plus C is partially miscible, A plus B is partially miscible, A plus C is completely miscible. Yeah, this type of systems really exist. So these are not like I'm just drawing for fun to make you understand something. Let's put one more system, C, A, B, and just imagine there is no line inside. So what does that mean? Which means this is completely homogeneous. So completely miscible, A plus B plus C, all are completely miscible. Homogeneous solution, which means separation is not possible. Separation is not possible. And then if you go back here, I already said somewhere, yep, I said this type of system as a type A system. So A plus B are partially miscible, and A plus C are completely miscible. B plus C is completely miscible. So we call them as a type 1 system. This particular image which you are seeing here, this is a type 1 system. We have something called as type 2. We will come back to that later. Yeah, I will show you how the type 2 system looks like, and how the temperature can change the liquid equilibrium from type 2 to type 1 system. So those things we will learn in the next lecture. So these are few things that you should understand. Yeah, so in case in the exam, if I give you a ternary diagram like this, say for example something like this one, CAB. So if I ask you to tell me, so which are the two components are completely miscible, which of the two components are partially miscible, then you should tell to me. Yeah? So in this case, B plus C is completely miscible, A plus B is partially miscible, and then A plus C is partially miscible. I think it's easy. I think it's not tough. So these are the things we learned, and then don't forget we are talking about liquid extraction. You should have some extract, you should have some raffinate, and your extract might contain 3 of your components, A plus B plus C, and your raffinate might contain 3 components, A plus B plus C. I showed you how to plot on a ternary diagram. You just draw the curve, and then you should C should go to the top of your triangle, A should come left, B should go to the right. Just for consistency, A is your carrier liquid, B is your solvent, and then C is your solute. Always try to follow this pattern, because when we are going to solve some problems, we need to, I will tell my feed solution contains 20% of C and 80% of A. So that time we are going to plot some line, something like we are going to plot some line in this inside this triangle. So that time we shouldn't do any mistake. So that's why I stick to this rule. CAB solute should go top, A should come left, B should come to the right. So this is your 100% B, this is your 100% C, this is your 100% A. We already talked about this, so try to follow this lecture. I think I summarized enough. So I hope you all know, if I give you some ternary diagram, you should be able to tell which of the 2 components are partially miscible. So thanks for listening.